Assalamu alaikum, students and friends. Welcome to Circ's 144th episode of Physics Video Tutorials. My topic is analyzing a rigid body in complete static equilibrium. That is, a body that has no translational and no rotational motions. So just stick around, watch and learn. The question is, a box of negligible mass rests at the left end of a 2.00 meter, 25.0 kilogram plank. The width of the box is 75.0 centimeters and sand is to be distributed uniformly throughout it. The center of gravity of the non-uniform plank is 50.0 centimeters from the right end. Question is, what mass of sand should be put into the box so that the plank balances horizontally on a fulcrum placed just below its midpoint? The non-uniform plank is 2.00 meters in length and it has a mass of 25.0 kilogram. Its corresponding weight, labeled W sub P, is 245 newtons. Notice that the line of action of W sub P passes through the center of gravity of the plank. And we label the lever arm D sub P as the perpendicular distance from the axis of rotation or the fulcrum to the line of action of the weight W sub P, which is equal to 50.0 centimeters or 0.500 meters. Take note that the fulcrum is placed just below the midpoint of the plank. All right? So our target variable is the mass m sub s of the sand. The sandbag's corresponding weight W sub s is represented here by the downward red arrow in the diagram. And the distance from the fulcrum to the line of action of W sub s is the lever arm that we need for our computation. And this is equal to 0.625 meters. All right? It's actually 62.5 centimeters. Okay? Now, how did we get this? Since the sand is uniformly distributed in the sandbag, the center of gravity of the sandbag is at its geometric center. And this geometric center is half of its width, or that is one half of 75 centimeters, all right, equivalent to 37.5 centimeters when measured from the left end of the plank. Hence, the lever arm d sub s is equal to 100 centimeters, all right, minus 37.5 centimeters, or that is 62.5 centimeters, which is 0.625 meters. Since we assume that the plank uh, is to be in complete static equilibrium, which means it must have no translational or rotational motion. So we say that the torque principle and uh, the fact that F net must be equal to 0, all right? These two conditions of complete static equilibrium will be applied here, all right? So the torque principle can be written simply as the counterclockwise torque must always be equal to the clockwise torque about a defined axis of rotation, which in this case is the fulcrum, right? Now, for the counterclockwise torque, it is just equal to the product of W sub S, or the weight of the sandbag, multiplied by its lever arm, D sub S, right? Which we can substitute as W sub S times the lever arm D sub S, or 0.625 meters. W sub S is still to be calculated, right? Now, for the clockwise torque, it is just equal to the product of the weight W sub P and its corresponding lever arm D sub P. That is 245 newtons times 0.500 meters. So when simplified, all right, um, or when we isolate the unknown variable W sub S, all right, we will have 245 newtons multiplied by 0.500 meters to be divided by 0.625 meters. So doing our math, we will get the value for W sub S equal to 196 newtons. Right? This is the weight of the sound box. And since what you're looking for is the mass of the sand that is put in this box, all right, we just multiply, or I should say, divide the weight W sub S, 196 newtons, divided by 9.8 meters per second squared, and we will get this mass of the sandbag equal to 20 kilogram, which is the final answer to the question. So, that ends our tutorial. Till the next episode, inshallah. Thank you very much for watching. Please follow me in my FB page, and please don't forget to subscribe to my YouTube channel.